Oh, you know we're getting in this. Nah,
Nothing can travel faster than the speed of light. That
clearly. Nothing except for something called Cherenkov radiation. Moving on.
is one of the most fundamental laws in all of physics.
And I'm gonna have to stop you right there. But also, hi, my name is Simon Tracer, and welcome to a reaction video of science, where I, first of all, mentioned the grading that I gave this video, which was a B-. I might change that to be worse, depending on how I actually fully analyze all of the things in this. My initial reaction was off camera, and I was like, I'm gonna find out whether or not let's get into it.
Yet, right now, the universe appears to be expanding faster than that because space itself is expanding. When we look out to distant galaxies, they all appear to be moving away from us at faster than the speed of light, what's known as superluminal motion. But Einstein, in his theory of relativity, famously showed that nothing can travel faster than the speed of light at
There are at least a dozen different reasons why we have calculated objects at distance to be able to be moving at the speed of light. The expansion of the universe and everything else. Objects moving away is assumed to be some correlative effect instead of, I don't know, properly simulating galaxies over distances, which, let's face it, the faster ones would be in the front, and everything else would be lagging behind, and that can sort of be maybe interpreted as a correlation to say stuff about things. We've really only been able to look up at the sky and be able to track all these things for a few hundred or maybe thousand years, depending on what you think. But truly, it's only been 100 years. So, grain of salt, maybe a couple hundred, I don't know. Who cares? It's been a short amount of time that we've been able to observe the universe. So, our facts are based off of what? Moving on.
300,000 kilometers a second, or 186,000 miles per second. And that is a speed limit that applies across the entire universe. At first, this does seem like it's a paradox, right, with a fundamental law of physics being broken here. But rather counterintuitively, it's not. And the key thing here is that this isn't about things moving through space. It's about what space itself is doing. And also asking this question of does the universe expand faster than the speed of light is also a little bit of a moot point because the expansion doesn't have a traditional speed either. It's like asking, am I heavier than I am tall? It just doesn't.
No. First of all, you have to think of how are they getting the assessment that there is things moving at a faster rate at further distances, and also that apparently that rate is accelerating, which I've in a previous video already said, of course it is, because the further you are away from other galaxies, the less gravitationally bound you are to them, so the faster you're able to go. But also, if you're affected by electromagnetic fields, which everything is, then the light from everything else should interfere with you, pushing you further away. So, you're held on less tightly, and you're pushed just as equally, or as more things are spread out, more light from stuff that may have been maybe behind another galaxy might reach you as well as stuff that's in front of that galaxy. So more light over time is now able to reach you, so it's an accelerating factor. That's a hypothesis they don't get into, as well as time dilation and other factors that people are so focused on. Although I don't believe in time dilation, the fact that she didn't mention it is kind of a plus in some circles and laziness in other circles. At least acknowledging the time factor should be part of today's natural communication about it, because people believe time dilation, and it's just not even part of the lecture or essay.
It makes sense to even ask the question. So in this video, we're going to dive into this cosmic loophole that seems to allow the universe to expand faster than the speed of light.
There's two... Okay, so the thing about the expansion of the universe is that it's possible that it's very much like an accordion or escalator, treadmill, where the entire thing is moving at a steady pace, and the further and further away you are, well, we have to do math for it's now 1,000 years in the past, and then it's 1,000,000 years in the past, and then it's 1,000,000,000 years in the past. So as we get closer to those further distances, we're going to have to calculate for it being further and further into the past. Which is a weird thing to have to do, because it's not all happening as if it's a diorama right in front of us. It's something that's like, oh, first of all, it took a certain amount of time for the light to get to us, and then, depending on the expansion of the universe rate, if that is a thing, and time dilation, if that even affects it, how much longer or shorter amount of time did it take for light to get to us? Obviously, if it's expanding, it would take longer. So light speed is, as we say, being regular, but that means something that is 1,000,000,000 light years away is not 1,000,000,000 light years in the past. It can be that it's closer or further away than 1,000,000,000 years by a factor of however many thousands of years or so. And then as you go into the extra distances, which is redshift really happens over extreme distances, not that close to us. And it's interesting to contemplate just how to math. What does it look like if a galaxy that is super far away is moving towards us? Well, we would notice it being like, let's say that the light from the many billions of years would have taken some time in order to get to us, but then the next signals would take less time and less time and less time as they get closer and closer. But with the expansion of the universe, would that relationship ever be possible to be just, it's still moving away, but it's actually like physical movement is away, but the expansion of space makes it moving away, but not as much. Or moving towards, but the expansion of the space has it so that it's moving away, but not near, instead of towards. So eventually that galaxy is going to collide with us, but the expansion of the universe makes it so that it's going to take an extremely long time for that to happen, if it ever happens. Huh?
First, about why galaxies themselves aren't breaking the speed of light, and second, why the expansion of space doesn't even have a speed limit. So let's start with what's going on with the galaxies themselves. Thanks to the observations of Edwin Hubble in the 1920s at the Mount Wilson Observatory in California, we've known that for galaxies, so islands of billions of stars out there in the universe, the more distant they are, the faster on average that they appear to be moving away from us. This is caused by the space itself between those galaxies and us here on Earth in the Milky Way galaxy expanding. And the apparent paradox in all...
Let's pretend that you use a second per second for the speed of an object, and then after that calculate for its speed depending on everything else. Every second that you're experiencing, let's say you imagine that you look at the galaxies over the course of 10 years, right? An object that is 1,000 years in the past will have that 10 years stretched over those 1,000 years of potential motion. So an object that is 1,000,000 years will have that 10 years stretched over that entire 1,000,000 years of potential motion. And again, an object that's 1,000,000,000 years or 30 billion years away could be having that entire expanse be part of its motion. So it's really difficult when you come up with these ideas of the expanding universe, because it means a meter at one point in time in history isn't a meter anymore. The light that started here now took an extra billion years to get to where it's going. We are not discussing this.
All
Why?
of this comes from the way we measure those galaxies. So the light waves given out by the stars in each galaxy have their wavelength stretched out as space expands. It changes the light to a lower energy and therefore a redder colour of light. Now thankfully molecules and atoms in those stars leave unique fingerprints on the light that they give out that act as way markers, so we can actually tell and measure how much the light has been shifted by. This is what's known as a redshift, and it's a very similar phenomenon to what we experience here on Earth, known as a Doppler shift. So like when an ambulance races past you with its siren on, you hear the siren as a higher pitch as the sound wave gets squashed by the ambulance motion towards you, and then you hear it as a lower pitch as it moves away from you and stretches the sound wave out. So when we see stretched out, redshifted light from galaxies, we could interpret that in the same way as the galaxies themselves moving. And for nearby galaxies, like what Hubble observed, they look like they're moving away from us at about 1,000 kilometers a second. But it's the most the same way as the galaxies themselves moving. And for nearby galaxies, like what Hubble observed, they look like they're moving away from us at about 1,000 kilometers a second.
Right. There's something about the expansion seems to be one way or another. People, the Science Asylum guy had the best explanation possible, although he does get it wrong still, although the least wrong, was the idea of approaching it by how many times will the entire universe double? At what point will that occur? Like, it'll double in 4 years? Or what? And based on the speed and whatever else, you can deduce something like that. But again, it's like, okay, for all these things that are going at crazy speeds and whatever else, it has to be that there is reasons for it being observed moving at these speeds. But the problem with accordions, they're all moving at the same rate, or one of those bendy straws, right? Basically the same principle as an accordion. You stretch it out, and each segment is moving at the same rate, but all segments throughout the entire distance is moving the most amount. And you can end up with the closest distance is moving the least amount, and further distances away are moving at greater amounts compared to the center. But it's still the same rate, meaning everything is still moving, all of it, the entire universe, at 1 second per second, or some multiple of that. Clearly, it's not 1 second per second, or 1 meter per whatever, but the point is that it's the same rate everywhere, which of course we know is false because galaxies have their own speed. So the question is, what is the relative speeds of all these things individual objects need to be, or individual sections of space are needing to be seen with their speeds and distances that progress over a certain time, but that those measurements still need to be recalculated into and backtraced for their time discrepancies. And also, if time dilation is to be believed, there should be a time dilation variant function with all of this stuff, which is another bunch of math that you can't just say the regular observations are good enough to give you a flat answer. It's just not. That you would think that it would be, but it's like it just isn't. It's more complicated.
But it's the most distant galaxies in the universe that cause the problems when we interpret redshift in this way. For example, take the galaxy GNZ11, which held the crown of most distant galaxy known for 7 years. It has a redshift factor of 10.603. That means that the light has been traveling through the expanding universe to get stretched by that factor for around about 13.36 billion years. But if you think about the amount of distance the light has covered in that time, correcting for the expansion of the universe, you find that it's around 32 billion light years. So if speed...
So for the amount of time that it had to travel, it seems like the distance that it had to travel. So there is a time discrepancy consideration with regards to the actual distance that the entire thing would have to have traveled. Hold up. It's three things have to be true. First of all, the distance that it is said to be. Second of all, the amount of time that we assume is associated with that distance. And the speed of light, or the speed of the spreading of everything else, and how that affects the speed of light through distant galaxies, or the area between galaxies. So, wait. Are you saying you're looking at an object that is 32 billion light years away? Or are you saying you're looking at an object that its light, in order to get to us, has been stretched for 32 billion years in order to get to us? Technically, hold on, I need to listen to this again.
For 7 years. It has a redshift factor of 10.603. That means that the light has been traveling through the expanding universe to get stretched by that factor for around about 13.36 billion years. But if you think about the amount of distance the light has covered in that time, correcting for the expansion of the universe, you find that it's around 32 billion light years. So
wait, in order for the light to be stretched that far, By normal standards, it would have had to have traveled 13 billion light years, or it had to have been traveling for 13 billion years, but the distance is almost three times as much. Light speed through space I can't tell you how much this is too this isn't the correct amount of details for me, and I'm someone who's in this. For someone who isn't aware of all these details, this is like, okay, sure. But for me, this is like, yeah, what's the other half of your essay? You don't have more.
If speed equals distance over time, that means GNZ11 has an apparent speed away from us due to the expansion of space of 2.4 times the speed of light, appearing to break Einstein's fundamental law of physics that nothing can go faster than the speed of light. But the key word in space of 2.
You realize light years is the time that light takes to it's a combined phrase of, it's the amount of distance light travels in years times a billion, whatever, but it's a billion light years, but you lost me.
0.4 times the speed of light, appearing to break Einstein's fundamental law of physics that nothing can go faster than the speed of light. But the key word in that sentence is appear. The galaxies themselves are not actually moving. It's the space between them that's doing something. The analogy that's often used here is it's like baking a fruitcake, right? And the galaxies are the little bits of fruit, the raisins in the batter. As you cook the cake, the batter expands, and the distance between each little raisin or bit of fruit gets bigger. But the raisins themselves, the bits of fruit, haven't been wandering around the batter. Although that isn't a perfect analogy, because galaxies do actually move with a speed because they are pulled slightly by gravity towards other nearby galaxies in clusters and groups. Like how
they're also, of course, having their own speed because of the initial conditions force them into their own projectile speed. If unaffected by anything else, they'll still have their own speed.
our galaxy, the Milky Way, and our nearest neighbour, Andromeda, are slowly being pulled together by gravity, colliding in the next few billion years' time. That is the galaxy's actual velocity, speed, motion through space. It's what we call their peculiar velocity, or local velocity you'll sometimes hear it referred to. Usually that's anywhere from around a few hundred kilometers a second all the way up to a few thousand kilometers a second. That's only around about 0.1% of the speed of light at a maximum. So galaxies themselves are definitely not moving faster than the speed of light.
Yeah, stupid buttons.
Not moving faster than the speed of light. What's actually happening is the distance between galaxies is getting larger as space expands, which brings me to part 2. Why the expansion of space doesn't have a speed limit. First of all, that speed limit of 300,000 kilometers a second that light travels at comes from Einstein's theory of relativity. It says that as you travel closer and closer to the speed of light, any energy that you put in to try and travel faster doesn't actually go into increasing your speed. Instead, it increases your mass. You get heavier.
So the best way to analogize the system is that if you had something that was, say, on one side of that expanding, stretching thing versus the center, and then versus something on the distant edge of the expanding thing, clearly towards the center would be one rate, and to the extra distance on the other side of it would be double that. So here's the problem. People can be just anywhere throughout all of this space. All of space has its own rate of everything spreading out and moving at its own pace. I'm still not convinced that all of this is something that is fully realized and understood and properly understood correctly because of a couple things.
A whole video before with more detail on why the speed of light is a limit. If you want to check that out, I'll link it down below. But what's key about Einstein's theory of relativity is that really what it's saying is that nothing can go faster than the speed of light when measured relative to something else, hence relativity. So two things have to have both locations and motions in space itself against which you can measure a relative speed between them. But for the expansion of the universe, it's space itself that's expanding. There's nothing moving through space for you to measure a relative speed.
It's literally the stuff through the galaxies, through the edges of space, between galaxies, whatever, blah, blah, blah. One galaxy versus another is what you're noticing moving. But instead of thinking of them as being the galaxies moving, you think of the entire fabric of the universe as being stretched, expanded, whatever.
In the same way that if I stretch this bubble, this hair tie, and I asked you what speed is it moving at, it would depend where you measured it relative to. So you'd find the ends move a lot faster than the middle, which barely moves at all. So it doesn't really make sense to ask what speed is the bubble stretching at. What you can say is that it roughly doubled in size in the space of, let's make the math simple and say a second, so that we stretched it to about 10 centimeters wide in the space of a second when it started at around about, let's say, 5 centimeters. If you run the maths on that, that means you get a rate of expansion of the bubble of 2 per second. It doubled in size. Now, unsurprisingly to no one, my bubble is not a perfect analogy of the universe, because...
Well, I mean, if you think of it as stretching, then yeah, you can think of it that way. And like I said, with the accordion, it's an illusion. It's not that things are actually moving that well. They can't. Apparently, they can be moving that far away, that fast away from anything else. But for stuff that's closer, they're not moving nearly as distant as quickly. Which is what seems to be a paradox, but is not, because there are more sections of space that are also expanding than the stuff that's local. Everything that's local has only one section of space expanding, maybe, but everything that's far away could have hundreds or billions of sections of space that are expanding at the same rate. So, with a multiplication factor, you think of it as all moving even more away over time. Now, it is a weird phrase that people say that there are some galaxies that we'll never see the light of. And the answer to that is no, you're wrong. The light will get to us. It depends on how long, but it hasn't gotten to us yet, and it may take another billion years or so before it gets to us. But that's simple. Just wait long enough and you'll get there.
Remember, the universe doesn't have a center. Space is expanding everywhere at the same rate. Again, I've made a video on this before, going into more detail. If you want to check that out, I'll link it down below. But what this analogy with the bubble does help us realize is that what we've measured here is not a unit of speed, right? It's not a unit of length divided by a unit of time. The unit we got was just per second. So just divided by time. The same is true when we measure the expansion rate of the...
That's not how that works at all. You literally mentioned space, which is the distance of the bubble versus the distance of something that's closer to the center of it, barely moves a millimeter, but the full length of it is the whole 5 centimeters. So technically it expanded, it doubled after a second, right? For the expansion of the universe, it'll double after a few billion years or something. So for the 13 billion years, it's doubled like 7 times.
Universe, we measure the distances to the galaxies and the speed they appear to be moving away from us, and the correlation between those two things gives us the expansion rate in a unit of a distance divided by time divided by distance. And just like with our bubble example, those two distant units cancel out and you get a rate in per second, a unit of...
I'm gonna have to stop you right there. What the hell are you talking about? No! You can't just say something like that. That is wrong. It is the amount of extra distance a area will experience growth per second. It's not, you can cancel out the distances and it doesn't matter. A megaparsec is an extreme, stupid measurement of distance that has to do with a certain number of light years and then multiplied by whatever it takes to make it a mega. And the amount of kilometers per second is the rate of its speed, and the idea of per second is how much it is changing over each second. That is the acceleration rate. You can't say the distances just cancel out. No, it's literally saying at stuff of 1 megaparsec, you experience this much growth. At a second megaparsec, you experience that same amount of growth. It is a tiny amount compared to the length that you're experiencing. Kilometers per second versus a megaparsec is like saying it's an inch for the planet gets bigger or the balloon gets bigger per inch for every mile you blow it up, or something. That doesn't make sense. No. It's saying that after a given amount of time, what the area of space experiences is this small section is now added to its diameter. We consider it to be this much longer after this much time, per this much distance that you're observing. So when you observe a multiple of this extreme distance, you then add on each of those 1 kilometer per whatever, or a certain amount of kilometers per second to that, and you have the whole thing expanding at that rate. So further and further distances have a rate that is multiples of that kilometer. So then it's like out here at 22, you add the 22 kilometers. Out there at 100, you add the extra 100 kilometers. This goes beyond... Okay, listen, I told you I might have to even lower the grade, because maybe there's things that I forgot to grade. This is one of them. I'm gonna read it again.
Rate of the universe. We measure the distances to the galaxies and the speed they appear to be moving away from us, and the correlation between those two things gives us the expansion rate in a unit of...
What the fuck is happening? Kilometers per second. Okay. The speed it's moving away for the amount of area that you're observing, megaparsec. There's no numbers on this diagram, by the way. Screw that. Let's not have any perspective. Who cares? Hubble constant, kilometers per megaparsec. Isn't it 77 kilometers per megaparsec or something? Where it's like a certain distance. A parsec is weird. If you translated it to after, I don't know how many distance of light years away, the expansion rate is at an extra kilometer. And as we all know, a kilometer is a very small fraction of what we would consider a light year. So you add that extra 100,000th of a light year or whatever to it. So it's like, take this measurement, add that. Can you tell the difference? This measurement, add that. It's not much. It's really not. For every inch, add a millimeter to your measurement. That's what you expect over time the distances to actually mean. So for the further and further distances you go, the larger that factor becomes. Instead of just kilometers, now you're working in add extra light year or something. Which still, in comparison to the entire distance of billions of light years, is not that great big of an expansion or whatever.
The distance divided by time divided by distance. And just like with our bubble example, those two distant units cancel out and you get a rate in per second.
I almost guarantee you I have researched this and it's not 1 per second something something. It's like 77 per second or whatever. And still, it's not just, you don't cancel out those distances. It's about an acceleration factor given to any given of this length of the space you're observing. It's hard to expect anyone else to explain it, but pretend that if you have someone on a train, the speed that they themselves are moving in the train is a small amount, the train is going an extreme amount, and for every distance you travel over time, that person will have traveled a certain distance in the train, but compared to the entire distance you have traveled, the total distance of that person's travel will be an accelerated rate in comparison to the total distance the train has traveled. Because the train isn't going as fast as the person. The person is adding their own speed to the train's speed. Now, does that make sense? You don't cancel them out. You don't end up saying, oh, everything, blah, blah, blah. No. You say the object and the backdrop are moving at a certain rate, and for their own motion, the total actual distance considered based off these two factors is what leads to them being seen as moving this far away. No. You can no scientist will look at this paper and be like, that gets a pass. Everyone would be like, excuse me. No. You can't do that. So you went from my initial assessment was based off of some other stuff. I did say maybe you didn't look at speed over time, distance, something. But I meant that as you look further and further away, you're looking into the past, which is an event that already has happened. You're not even looking at that, and you're getting something else wrong. This is now a C, not C+. It was a B-, now it's a C. You've gone down 2 marks for this one mistake. Actually, it should be C-. This is a huge mistake. This is what we call in science a gross error. And in science communication, a great disservice to anyone paying attention, trying to learn these things. They're going to quote this to someone and someone will actually whatever else. If it ever mattered, it would be like, oh, you missed by an inch, you missed by a mile. You are off by so much with this. It's upsetting.
A unit of divided by time. And that is why even asking the question of is the universe expanding faster than the speed of light just doesn't make sense, because you don't measure a speed. It is like asking, am I heavier than I am tall?
And that's where I feel like somehow you got lost in the sauce. You don't understand acceleration rate. You don't understand how the measurement is actually... You don't cancel that shit out. And so, yeah, no, you get a C-. And in fact, you look crazy right now. For this one topic. Just this one thing. It's like saying the number of carrots you eat in a year plus the number that they pocket away, like every baker's dozen, you have the extra amount that you make, because clearly we're going to still be making the amount that we said that we were going to make with the amount of ingredients, but it might end up being a baker's dozen.
So what all of this means is that yes, at large enough distances, galaxies will naturally look like they are moving away from us faster than light. Not because they're breaking the laws of physics, but because the laws of physics were never meant to be applied in that way. But all of this has a very cool consequence. There are galaxies out beyond what's known as the observable universe that we will never be able to see.
That's the part I hate the most, because we will definitely be able to see them. If it's a trillion light years away, then it will take certain another 10,000 years or whatever, and the light will have gotten to us. So we will see it. Not in our lifetime, but we will see it. It's something vastly further than we've ever seen prior, or thus far, and even assumed to see with the Hubble Space Telescope. I don't I don't agree with the amount of billions of light years and the amount of billions of years assessment on face value. Again, there's still no reference to time dilation, which is like the dogma of the age. Everyone talks about time dilation. You can't just say it doesn't occur, or it's not part of the maths that you're using, because like that's just bad scientific method according to literally everyone else in the method. So then what part does time dilation have to do with all of this nonsense? And does it? And apparently, no, it doesn't. But it's the fact that the space is just becoming more. So an inch wasn't an inch a billion years ago. It was a billionth of an inch, or something. It was some other number, where it's like now a light year was an inch. So like given the extra amount of time that it took for the light to get to us, even at the speed of light, it took extra time for it to get to us because of the space making that distance even that farther away, because of how long it's taken to travel through that space and how that space has become wider and wider and wider, or further and further away from us. No, I'm changing it to a C.
Now, if you love mind-bending physics like this and want to get more familiar with the background science that underpins problems like this, then I highly recommend that you check out Brilliant, the sponsor of today's video. Brilliant helps you excel at science, maths, and coding, whether you're 10 years old or 110.
I hope you're not learning from this, and this is what teaches you this bad logic. Because that means that this entire company of Brilliant needs a stern talking to. Because they are a business shilling a bunch of textbook stuff that's just not based from reality. Not actually looking at everything from the full dynamics. Because, like, seriously though, radiation pressure. Didn't mention it. The stuff moving at its own rate and whatever else literally is the rate of which we look at all things. We think of it compared to us and our motion. And our motion is still rated to be on a galaxy that has its own motion through space. So we consider our movement and how long we've traveled through space and how far everything else seems to be moving. We're moving relative to the past, which is a fixed position. Don't think you shouldn't understand that. That everything in the past is where it was, right? And then when you look at other things from distant things, you're looking into a further past. So it took a billion years ago is when those lights But it's apparently with the expansion of the universe, it's not a billion years ago that those lights came from there to get to us. It's apparently 30 billion years ago or something that it took for the light to get to us or something like that. Figuring out stuff with the distance and math of super distances is crazy. It's nutty. And I am unfortunately going to have to change your grade. The question is, at this point, should I give a C minus or a D? Can I fault people for just going by the textbook? This is not even the textbook! This is ignoring textbook and having random thoughts of just ignoring the distances over the distance thing. Like, I'm sorry, what? Yeah, no, it's add the kilometer per second for every, add an extra kilometer to every for every extreme distance, you add 1 kilometer given a certain amount of time, right? And I think it's 77 kilometers per second per megaparsec. So it's like, for every extreme distance, there's this rate of expansion, which is 77 kilometers per second. If you were to say, take that same measurement of 77 kilometers per second and apply it to half the distance, that means for the same 1 parsec, you would have twice the rate. You need to establish the rate for the area to get the correct total amount of added stuff per distance. It's a convoluted way of saying an acceleration rate, but it's still an acceleration rate. I have to wonder if the body of work that she has versus the actual information and the things that she got wrong, I can't fault that deeply for things that people in general, the textbooks, don't have correct. But when you're saying some things, I'm like, I'm stuck between giving a D or a C minus. A B minus is already bad. That's not great for a professional. You shouldn't do that. And that's based off of some of the basic things that I noticed getting wrong. That other thing adds another extra, like, this is not even the correct scientific method of how you handle things, whatever, with this math. It's what you do say that matters, not what you may or may not be aware of. So I'll give it maybe 2 ratings. What is reality versus what you are aware of? Okay, so look, no one has corresponded back to be aware of, okay, where are you getting this information? How are you making all of this assessments? I've been in this for 15 years. I'm aware of all of the bunk that people are saying in the textbooks and the many things that people have gotten wrong and the many things that are the dogma of this age that is what you should be saying according to the majority of scientists, and then you're getting it wrong even then. So that's a C minus. I'm sorry. It's nice to think of, yeah, the universe expanding and whatever else, but this is not the correct information. So I would love it for you to learn the correct information, and I would love it for you to give a retraction. You don't have to say that I gave you any of these pointers or whatever else, but it's like, listen, of all the people that I have ever given any effort towards, one person wrote back. Just one. Okay? I'm fine with them. They're not my students. They're not people that I would actually have any, like, we're not in the same circles or anything like that. I'm not recognized literally anywhere except for on the freaking internet. I only know what I am absolutely taking in from anywhere that I can and everywhere that I've been able to over the course of decade. And it's not easy picking and trying to figure out, well, okay, space-time said one thing, but then it gets updated over a certain amount of time, and you have to rewatch all of the stuff in order to try to figure out what people are in general saying about all of this, given the body of information about all of this, which is nonsense. The actual stretching thing, that's big. Everyone says about the stretching, and they forget, yeah, no, this is a rate of acceleration for a given area. And that rate happens in every section of area, which she said. She said that with all this space expanding and everything else at the same rate, the Doppler effect is a good effect to mention, and it's a good explanation of that. That's fine. You don't get A- marks for Doppler effect. Except for there's a couple of questions about how the Doppler effect truly occurs, which is a nuanced type of thing that I'm not going to bother you about, although I'm still bothered about it, because you might be saying it right, but the mechanism of how it goes about isn't just that the space is expanding. Light has the Doppler shift effect because of quadrillion light years or something. It's a ridiculous large amount of distance. So it's like, whatever. Yeah, no, the major problem that is insanely impossible for anyone to get correct and state in one of their videos, besides some, like, towards other scientists, is as you look into the past, you're not just looking at stuff as it is now, you're looking at stuff as it is, as it was. And that stuff is a signal that appears now as something that is now moving at a certain rate. But it's crazy because if you think of everything as the same, like, if light was instantaneous, for example, then all the information from all of time, or if light, how do I put this? If light from any given position in space takes like an exact amount of time that all of the actions of a second per second were to be visualized as a second per second here, all of that breaks down the moment you go anywhere past a light year or anywhere past Pluto. Like, the stuff that's happening over on the sun is 8 seconds old information. So if something happens, or 8 minutes old information, that information is not useful if the sun suddenly decides to explode. We won't know about it for another 8 minutes. And all the stuff happening with the galaxies and stuff that's happening, if it's 100 or 1,000 or 1,000,000 or 1,000,000,000 light years away and in time, then it's happening the extra distances away, the extra amount of time into the past, and the amount of time or the entire amount of distance, if it's expanding, then makes it so that all of that our time that we expect for light to pass means that the speed of light, although is consistent, is still something that's like, because it's not just distance into a further away from us, it's a distance for the past. Stuff that's moving 1,000 light years away could be moving and seen as moving 1,000 times faster. That doesn't make sense. Or something that's how does it really work? If you see something move a meter and it was 1,000,000 light years away, it took 1,000,000 light years for that, or it took 1,000,000 years for that light to get to us to show us that a meter has happened. But does that actually reflect its own distance and speed? As I said, it's nuanced. It's hard for me to grasp my head around it. Without the proper concepts of it, it's hard for anyone to properly communicate about it. So it's ignored by mostly everyone. Whatever. The only thing I can hope is that someone is going to be like, okay, wait, you're basing all of this, you have all these other bits of information, and some of it might be right or wrong, but you are able to say things that, yes, if I checked correctly, okay, I was wrong about certain things. and whatever else. And as long as it enriches their life to make better choices later, or make better assessments later on, or whatever on something, that's all that really matters. But like, I'm still having to make these essays, these reviews. I'm still having to make these corrections and grade all of these videos. That's really what I can do. It doesn't matter if I find videos that are right, wrong, or whatever. I'm here to grade all the videos based on of accuracy to the craft, accuracy to like the dogma, and then accuracy to reality. And it's like it almost feels unfair to grade something versus reality, because like I said, there's a complete divide between the textbook and what's actually out there. Even though we're working for over 100 years with the best scientists, whatever else, and NASA to try to figure all this stuff, and we're all wrong. With very few exceptions of us. Science Asylum guy, very close. He got my high. He is one of them who got one of my highest ratings ever. Still was wrong, slightly. Still missing some parts. There's nothing wrong with that. It's just how we learn things. But if you're going to make a professional statement, you've got to not have these mistakes. But I can't fault people for not knowing everything. I'm a generalist. I learn everything. I assess everything. It's not just physics and the stuff with time and everything and space and electrons and whatever else. It's literally everything. I consume all knowledge. And then be like, yeah, no, you should have remembered or noticed this part of the assignment. No one reads that part of the book. Or cross-references all the different bits. Like, they get the idea of electromagnetism and they forget how it works on protons. They think of it working on electrons only. Electromagnetism also works on protons because they're positive. How does the electromagnetism work on a proton of a mass scale? That's gravity. Whoops! Very similar relationship, where it's a lot weaker on protons. The electromagnetic field still has some effect there. If I haven't said it already in this video, I probably said it in the other video about the idea that I did say radiation pressure. The radiation pressure is like literally all of the light pushes everything else away. So, again, the more spread out everything is, the more of that light can actually get to you. It's not more diffuse, so there's less of it. It's less shaded by other things, so more of it gets to you. That's a counterintuitive thing to think, because like when it's all compressed, when everything was in a smaller ball, all of light was hitting and being absorbed by everything that's in front of you, between you and the source. Once you're spread out enough, all of those sources can hit you simultaneously now, in a larger area. So it's like you're being hit with a greater and greater amount of force. That's why it's an acceleration rate that's also increasing. What is the correct... I don't know the correct term for an acceleration rate that is going up. Right? How to explain an acceleration rate that's going up? Let's say that you're moving 10 kilometers per hour. In the next hour, you're moving an extra 1 kilometer per hour. So you went from moving 10 kilometers an hour to now 11. In the third hour, shut up, you will be moving 12 kilometers per hour. In the next hour after that, you'll be moving 13 kilometers per hour. And so on until the point where you're moving 20 or even a light year per hour. The acceleration rate is saying, the acceleration rate going up means that instead of just 1 per second or 1 per hour added, it's not just 1, it's 1 plus a ratio of the amount added each time or something. Exponential growth. Something like that. Where it's like instead of adding 1, after a few hours, now you're adding 2. Instead of just 1 per hour. So once you get to 20, now you're adding 2 per hour. So the difference between the 0 hour and 1 was 1 extra per hour. The difference between 10 and 12, or 10 and 11, is 2. The difference between 20 and 21 could be 3, it could be 5. So now, instead, you're ramping it up. Right? Instead of going at the same pace and increasing at that rate, it's now increasing more as it increases. Which is why they say the weird thing of seconds per second. It's an acceleration factor. Whatever. Blah, 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 blah.